graphing, but now we're going to be intentional about finding specific points. We're going to be looking for roots. Roots are where it crosses the x-axis. We've used this term in other situations. So one of our objectives is to understand the difference between a quadratic function and a quadratic equation. It's very simple. Then, as I've alluded to, what is a root? Then how do I find roots on a graph? And then how do I find roots on a table? A quadratic equation is a function where the f of x or y is replaced with a value. When we're in standard form, the value is 0. Okay, so we don't have an f of x or a y. Instead, we have a 0. What we're used to seeing and what we're still graphing is f of x is equal to ax squared plus bx plus c. Now we've taken out f of x. Take that out and replace it with 0. Okay? Sometimes in your assignment, you're going to have to make sure you're in standard form. That means all the terms are on one side and the 0 is on the other. It doesn't matter which side it is, it's just all the terms have to be pushed onto the same side. When you have an equation, and it's set equal to 0, you are being asked to find, it is implied that you are being asked to find the roots of the equation. This is where the graph crosses or touches the x-axis. We have referred to them in linear and absolute value as solutions, zeros, x-intercepts. These are all interchangeable words for roots, and they are where it crosses the x-axis, so they are the x-intercepts, so we're going to write them as intercepts. Sometimes we won't get nice integers and we will have to estimate the solutions. If we are estimating, we will say something like, oh, x is between 1 and 2. Okay? We don't have the exact root, so we don't write it as an ordered pair. Let's determine them from a graph first. So quadratic equations can have one real solution, two real solutions, or no real solutions. Okay? This is an example of one real solution. They don't have to be integers. Okay, I just did integers to make it easy. All right, this graph comes down, touches the x-axis, and goes back up again. It touches at what is labeled -1, 0. So the solution is -1, 0. This graph has two solutions. It crosses at 0, 0, that's a solution, and 4, 0, that's a solution. Two real solutions. Okay. And then we have no real solutions. That means it misses the x-axis entirely. Okay? And then we could have no real solutions like up in here, right? We could have two real solutions like in here, or one real solution like this. There's lots of possibilities, okay? But the big picture is it could touch, which is one solution, it can cross, which is two real solutions, or it can miss, which is no solution. All right. We can also determine roots from a table, all right? So the easiest thing to do is first look for where you have a y value that is equal to 0. So notice I have here and here. When you have that, and you won't always, you have exact roots. They are at 1, 0, and 4, 0. These are exact roots. If you don't have exact roots or an exact root, then what you have to do is you have to look for where the y values change signs. They might go from negative to positive, or they might go from positive to negative. If the y values, for instance here, is positive 3, and then it crosses over to negative 6. Well, what value did it have to cross through? It had to cross through a 0, okay, or a root. So we would say, we would estimate the roots. The root is between, and then we report x values. Report x values. We don't say the root is between 3 and negative 6. We look at the y values, but we report the x values. The root is between 1 and 2. Now look at this green situation here too. Notice that this goes from negative to positive. In order for that to happen, what did the y value have to cross through? A 0. So we would say root is between 1 and 2 and 3 and 4. Again, when you're estimating, you look at the y values, but you report the x values. Third situation is if all the y values stay the same. Not the same number, but the same sign. Then there are no roots. Okay, so my lowest y value is 2, and then all my y values are higher from that. So it's never going to cross the x-axis. It's always going to be above it. If these were all negatives, then it would stay below the x-axis and not cross it. Now what we're going to do is we're going to graph our function and find the solutions to the equation by looking for y values that have a 0, okay? So let's go through this. We're going to graph it just like it was our function before. See, look, I even wrote it as a function down here in my table. We're gonna graph it like it's a function. Okay. All right. Let's see. I have a 1. B is negative 3, and C is negative 4. Why don't you go ahead, hit pause, and fill in, everything up to the table, so 2 through 6. Okay, so A is 1, so this is going to open up because A is greater than 0, which means that my vertex is going to have to be a minimum. That's going to help me with the range. My y-intercept is 0c, which is 0, negative 4. The axis of symmetry and the y coordinate of the vertex are all both found by using the formula the opposite of b over 2a. So we have the opposite of negative 3, which is positive 3, over 2 times 1 is 2, so we get 3 halves. So I'm going to go ahead and put that on my graph now. This is my axis of symmetry. It's going to go in between these two lines. X equals 3 halves. Then I'm going to plug that in to my equation to find the y-coordinate of my vertex. So I get 3 halves squared minus 3 times 3 halves minus 4. So I get 9/4. When I multiply negative 3 times 3 halves, I get negative 9 halves, which is the same as negative 18/4. I'm doing that so I can have a common denominator. And then when I convert negative 4 into fourths, that's negative 16/4. So my vertex is the point 3 halves, negative 25/4, which is negative 6 1/4. My domain is negative infinity to positive infinity. And my range, this is a minimum, so my smallest y value has to be the y-coordinate of my vertex, negative 25/4, or negative 6 1/4, all the way up to positive infinity. All right, now we're going to fill out our table. My vertex is at 3/2. I don't do the calculation again. Negative 25/4. I'm going to put in my y-intercept 0. So that's 0, -4. All right, so 1.5 and then 6 1/4. 1, 2, 3, 4, 5, 6, negative 25/4, and then 0, -4 right here. Now I'm going to use symmetry to get my point on the other side of that. So that is 1.5. So that takes me to 3. And then I use symmetry. And then I'm going to plug in, let's see, -1. So that's 1 plus 4. -3 times -1 is +4. Sorry, that's +3. And then -4. And so I get -1, 0. And see, this is what I'm looking for right here. That's the difference in what we're doing today. I'm looking for those points where my y-coordinate is 0. And when I find an exact one, that's good, because I won't always get an exact one. Then I'm going to use symmetry to find the other point on the other side. So this is 1 space, 2 space, 2.5 spaces to the left. So now I'm going to count 2.5 spaces to the right. 1/2, 1, and 2. And so that is the point 4, 0. I'm going to trace my graph and write my solutions. -1, 0, and 4, 0. This next one is not in standard form. We have to get it there before we start solving. So we're going to rewrite this as x squared plus 8x plus 16 and identify a, b, and c from that. A is 1, b is 8, c is 16. This is going to open up because a is greater than 0, which means that my vertex is going to be a minimum. My y-intercept is 0, 16, so that's pretty tall, so I'm going to set my scale at 2's. My axis of symmetry, the x-coordinate of my vertex, is at -8/2. That's -4. So I'm going to put my axis of symmetry in red. This is -2, -4, so here it is here. And now I'm going to plug that into my equation. I'm going to use this version here. So I have -4 squared plus 8 times -4 plus 16. And when you do that calculation, this becomes +16 plus 16 is 32, and this is -32, so I get 0. So I get the point -4, 0. That's my vertex. All right, and notice what my y value is. I have found my solution because the y-coordinate is 0. So I have -4. Sorry about that, I went the wrong way. I have I've gotten to this point 5 times already. I do not want to start over again. Right? This is a key point for us. Our domain is negative infinity to positive infinity. My range, this is going to open up, so this is going to be my smallest y value, so that's 0 to positive infinity. And now I'm going to make a table. My vertex is negative 4. When I plug in negative 4, I get out a 0. I'm going to use my y-intercept is 0. And then I'm going to use negative 8 because that'll be the symmetrical point. Can't hardly read that. And then symmetry, I don't understand. Negative 8, 16. So I'm going to plot these points. I already know what my solution is, so I'm making my life easy here. And then 2, 4, 6, 8, 10, 12, 14, 16. And then count over two squares here. And then draw the graph. And then identify the solution. Just like that. Right? This is the last one that we're going to do. Again, it is not in standard form, so I'm going to rewrite it as x squared plus 4x minus 1 equals 0. Here I'm going to write it as y equals x squared negative x squared plus 4x minus 1. A is negative 1, B is 4, C is negative 1. It's going to open down because A is less than 0 or negative, which means that my vertex is going to be a maximum. My y-intercept is 0, negative 1. My axis of symmetry I find by using the formula negative b over 2a, and I get the opposite of 4, negative 4 over 2 times negative 1, negative 4, negative 2. So then I get positive 2. So my axis of symmetry is at positive 2. I'm going to now calculate the y-coordinate of my vertex. So I have the opposite of 2 squared plus 4 times 2 minus 1. 2 squared is 4. Opposite of that is negative 4. Negative 4 plus 8 is positive 4. Positive 4 minus 1 is equal to 3. So I have the ordered pair 2, 3. My domain is negative infinity to positive infinity. My range, this is my highest value, so I'm going to go from negative infinity to 3. And now I'm going to make a table. My vertex is at 2, 3. One, 2, 1, 2, 3. Here's my vertex. My y-intercept is at 0, negative 1. I'm going to move this up because I'm going to want to find a point in between. Okay, so that means at 4, -1, because I know I have a point directly across from that, so I know I have 4, -1. And then I'm going to plug in a 1. So y equals -1 plus 4 minus 1. So that's going to give me 1, 2, like here. And symmetry is going to give me 3, 2. And so my solutions, my roots will be between 0 and 1 and 3 and 4. Between 0 and 1 and 3 and 4. Because here this is going to be at 3, 2. Okay. All right, we're going to work on these problems in class tomorrow. So I will see you then. Thank you for listening.